My name is Nidhi Chauhan. I'm assistant professor at Gyan School of Pharmacy, that is a part of the Suresh University, Jaipur. So today we are going to discuss this carboxylic acid, and this is in your pharmaceutical organic chemistry first and your second semester. So the learning objective is the learning objective of this topic is that here we are going to study about the carboxylic acid and as you all know, in the last few videos, I have already told you that what are the carboxylic acids, and also we are going to learn about the method of preparation of halo acids. The halo acids also comes in the category of this carboxylic acid, and they are the derivative of this carboxylic acids. And this halo acids means that the halogen is present on the carboxylic acid. So here we are going to study about the method of preparation of halo acids, and also we are going to study about the chemical reactions of this halo acids. And the student outcome, they will be going to know about carboxylic acid, its derivatives, and also they are going to learn about the preparation method of halo acids. And they are also going to learn what are the chemical reactions of these halo acids. Halo acid generally means the halo and the acid. Halo means halogens and the acid. When the halogens are present on the carboxylic acid, that forms this halo acids. Let's start the reactions of carboxylic acids. As I have already told you that these are the reaction sites of the carboxylic acid. Carboxylic group of carboxylic acid means the oxygen are having the lone pair present on it. So the electron deficient species will attack this oxygen because it is carrying a lone pair on it, and the electron deficient species is your electrophile, that is a proton which need electron having the positive charge on it, and that is why it will attack to this oxygen. Secondly, the acidic proton, the acidic proton targeted by the bases. So the bases are being targeted by this uh, acidic proton. So here, thirdly, it is a electron deficient carbon targeted by the nucleophile. So here, the nucleophile will attack to this electron deficient carbon because it will be having the positive charge on it. Then this oxygen will withdraw the electron from this carbon. So this electron deficient carbon will be targeted by the nucleophile. Next is your reactions of carboxylic acid can be placed into four categories. So here, first is the reactions at the acidic hydrogen. Secondly is the reaction at the carbonyl group. Thirdly, reaction at the carboxylate oxygen. Fourth, reaction that leads to loss of the carboxyl group as CO2. So here, the CO2, whole CO2 will be removed out, means that is known as your decarboxylation. When the CO2 removed out, so that type of reaction is known as decarboxylation. Next is your method of preparation and chemical reactions of halo acids. So the method, how these halo acids are prepared and what type of reactions they are showing. So the hydroxy acids, halo acids, amino acids, and nitro acids are the derivatives of this monocarboxylic acid and are known as substituted carboxylic acid. So these hydroxy acids, these halo acids, and these amino acids and nitro acids, these are all are the derivatives. Means if the hydroxy group is present on this carboxylic acid, this is also the derivative of the monocarboxylic acid. Secondly, if the halo means a halogen is attached to this acid, carboxylic acid, and that they are known as your halo acids. Thirdly, nitro acids. If the nitro group is present on the carboxylic acid, then that is known as your or carboxylic your derivative of your carboxylic acid. Next is your amino acids. Amino acids, if the amino group is present on the carboxylic acid, then that is also known as your or halo acids. They are known as substituted carboxylic acids. They are known as substituted, means there is a substitution on the this carboxylic acid chain, and these hydroxy, halo, amino, and the nitro gets will substitute the hydrogen from the chain of this carboxylic acid and get substituted on that place. So first method is your preparation of halo acid. So the first method of the preparation of halo acid is Hell-Bullard Zelinsky reaction. So in this aliphatic carboxylic acids on reaction with bromine in the presence of phosphorus produces alpha halo acids. Reaction is known as Hell-Bullard-Zelinsky reaction. So in this, the aliphatic carboxylic acids on reaction. So the aliphatic carboxylic acids which are present, which are having the hydrocarbon chain, they are reacting with the bromine, and in the presence of your phosphorus produces alpha halo acid. So on the alpha position, a halogen will get attached, means that bromine will get attached, and this reaction is known as your Hell-Bullard-Zelinsky reaction. So here you will study that the propanoic acid, which is your carboxylic acid, aliphatic carboxylic acid, as you can see that the hydrocarbon chain is attached with this carboxylic acid. When this is reacted with this bromine, in the presence of this red phosphorus, then there is a formation of this 2-bromopropanoic acid. Means on the second position, on the first position from this function group, where the function group is attached, that position is your alpha position. So that is why its name is alpha bromopropanoic acid, or you can say the 2-bromopropanoic acid. So when the these derivatives are formed from the substitutions of this hydroxy, halo, amino, and the nitro on the aliphatic carboxylic chain. Then they are known as your derivatives of monocarboxylic acid, or known as substituted carboxylic acid. And the preparation of halo acid is first that Hell-Bullard-Zelinsky reaction. So in this, the aliphatic carboxylic acid, when we are reacting this aliphatic carboxylic acid with this bromine, and in the presence of your phosphorus, the red phosphorus, then it produces alpha halo acids on. And this reaction whole reaction is known as your Hell-Bullard-Zelinsky reaction. So in this, the propanoic acid is reacting with this bromine in the presence of the red phosphorus, and there is a formation of the alpha bromopropanoic acid. So here the 2-bromopropanoic acid is formed, that is also known as your alpha halo acid, or you can say that alpha bromopropanoic acid. Next is your second reaction is your hydroxy acid. So alpha halo acid can be obtained by the treatment of alpha hydroxy acid with HCl or HBr. So this is your alpha halo acid. This is your alpha hydroxy acid, that is your lactic acid. And when we are treating it with the HBr, means the hydrogen bromide, then there is a formation of this 2-bromopropanoic acid, or you can say the alpha bromopropanoic acid. So here, from this alpha hydroxy acid, we can also prepare this alpha halo acid. So this lactic acid is your alpha hydroxy acid. When it is treated with the HCl or your HBr, then there is formation of this 2-bromopropanoic acid, or you can say that 2-chloropropanoic acid is formed here. Next is your alpha beta unsaturated aldehyde. So here the third reaction is this, that alpha beta unsaturated aldehyde on reaction with halogen acid followed by oxidation produces beta halo acid. So on the oxidation also the beta halo acids are formed. Means on the oxidation of this aldehyde, there is a formation of this halo acids are formed. So from this alpha beta unsaturated aldehyde, unsaturated means there is a double bond in this aldehyde on the alpha and the beta position. So as acrolein is the example of this alpha beta unsaturated aldehyde. When it is first reacted with the hydrochloride, that is the HCl, then there is a formation of um, this chloroaldehyde is formed here. After that, it get oxidized, and there is a formation of this carboxylic acid. As you know that the aldehyde get oxidizes in the presence of the oxidizing agent to this carboxylic acid. From here, when there is a formation of this alpha, this beta carboxylic, beta chloro propanol. Then after that, it is oxidizes and there is a formation of this beta chloropropanoic acid is formed here. So here, these are the reactions of this um, alpha preparation method of this alpha halo acids, and next is your or by alpha beta unsaturated carboxylic acid. So by alpha beta unsaturated means they on the alpha and the beta position there is a double bond on this carboxylic acid, and when it is reacted with these halogens, they are forming this halo acids. So here alpha beta unsaturated carboxylic acid carboxylic acids on reaction with halogen acids produces halo acids. So this crotonic acid is your alpha beta unsaturated carboxylic acid, and there is a formation when it is reacting with this HBr, then there is a formation of this beta bromobutyroic acid. So there beta bromobutyroic acid is formed here. So as you can see on the beta position, this bromo is attached. So that is why its name is beta bromobutyric acid. Butyric acid. Or you can say that beta bromobutanoic acid. This is the common name of this compound. Next is your by the reaction of sulfuryl chloride on carboxylic acid. So when this sulfuryl chloride is reacting with this carboxylic acid, then there is a formation of this propanoic acid, means there is a formation of the alpha halo acid. So reaction with SO2Cl2, that is the sulfuryl chloride, in presence of your iodine carboxylic acid gives halo acid. So this carboxylic acid gives halo acid. So this propanoic acid is reacting with this sulfuryl chloride in the presence of iodine. There is a formation of this 2-chloropropanyl chloride plus sulfur dioxide plus HCl. So this 2-chloropropanyl chloride is boiled, and there is a formation of this 2-chloropropanoic acid is formed here. So in this, by the reaction of sulfuryl chloride and carboxylic acid, firstly, on the reaction of this propanoic acid to the sulfuryl chloride, there is a formation of this 2-chloropropanyl chloride. Means the chloride is attached to this position, on this propanoic acid. And after that, when the boiling is done, then from this, the chlorine which is attached to the CO carbonyl side, this get removed and the OH will get placed to it. Means it is get substituted to this position, and there is a formation of the alpha halo acid. So this alpha halo acid is formed in this method of preparation of this by the reaction of the sulfuryl chloride and carboxylic acid. So these are the 5 reactions that occur from this method of preparations of this halo acid. So in this method of preparation of this halo acid, first is this hal Volar-Zaleski reaction. In this, the aliphatic carboxylic acid on reaction with your bromine in the presence of phosphorus produces alpha halo acid, and this reaction is known as the hal Volar-Zaleski reaction. And in this, the propanoic acid is reacted with this bromine, and in the presence of this red phosphorus, and there's a formation of this 2-bromopropanoic acid. So this is the or you can say the alpha bromopropanoic acid is formed here. Secondly, it was your by hydroxy acid. So in the hydroxy acid, this alpha acids, hello acids can be obtained by the treatment of alpha hydroxy acid with HCl or HBr. So here, this alpha, this lactic acid, which is the alpha hydroxy acids, and is this alpha hydroxy acid is reacted with this HBr, that is your hydrogen bromide acid, and after that there is a formation of this alpha bromopropanoic acid. So this is also a derivative. This is also a alpha bromopropanoic acid, or you can say that 2-bromopropanoic acid, because the bromo is attached to the second position of the this chain. Here you can see this is your because your function group is attached, that is why this is the alpha position and this is the beta position. So the bromo is attached to the alpha position. So this is your 2-bromopropanoic acid. Next is your by alpha beta unsaturated aldehyde. Alpha beta unsaturated aldehyde on reaction with halogen acid followed by oxidation produces beta halo acid. So in this, firstly the alpha beta unsaturated aldehyde has to convert it into the halogen acid, and after that there is a oxidation and there is a formation of this beta halo acid. So here you can see the on the alpha and the beta position to this aldehyde, alpha and the beta position of this aldehyde, this HCl is reacted and this is formed on the this position. After that, after after the oxidation, this aldehyde get converted into the propanoic acid. This oxidation of the aldehyde to the this carboxylic acid we have already studied in the method of preparation of carboxylic acid. Next is your by alpha beta unsaturated carboxylic acid. So in this, the alpha beta unsaturated carboxylic acid on reaction with halogen acid produces halo acid. So in this, alpha beta unsaturated carboxylic acid means the alpha and the beta position is having the double bond. Unsaturation means the double bond is present. After that, this carboxylic acid is attached to it, and on reaction it with the halogen acid, it produces halo acid. So here the halo acid is formed here. So here the beta Br, that is your bromo, is attached to the beta position of this carbon of this acid whole aliphatic. That is why here this bromo is attached to this beta position, because this is the carboxylic acid and this is the alpha position and this is the beta position. So this, its name is beta bromo butanoic acid, or you can say that beta bromo butyric acid, and here it is attached to the third position. So 3-bromo butanoic acid is also called 3-bromo butanoic acid. Next is the by the reaction of sulfuric chloride on carboxylic acid. So here the reaction with SO2Cl2 in presence of iodine carboxylic acid give halo acid. So in this you can see that this propanoic acid is reacting with this sulfuric chloride in the presence of iodine, and there is a substitution of this chlorine on the two position, that is from here on this position and on the this position. So here its name is 2-chlorochloropropanoid chloride, and SO2 sulfur dioxide is formed here and HCl is formed here. Again this 2-chloropropanyl chloride is again boiled and in the presence of this water, and there is a formation of this 2-chloropropanoic acid. So this chloro is removed from here, and when this H2 is associated with H positive and OH negative, then OH negative will attach to this position, and this H will get attached to the C that is removed from here. So here 2-chloropropanolic acid is formed here. Next is the biochemical reaction of halo acid. So here the halo acid shows the similar properties as carboxylic acid. So halo acids are also give the reaction of halogen group. The main reaction of halo acids are as follows. So here halo acids are also showing the similar properties The properties that are shown by the carboxylic acid, that properties are also shown by this halo acid. So these halo acids are also give the reactions of halogen group. So these halo acids are giving the reaction of halogen group, and the main reaction. So the main reaction of this halo acids are as follows. Firstly, it is your acidic strength. So in the acidic strength, the halo acids are more acidic than carboxylic acid. So these halo acids are more acidic than the carboxylic acid because halogens are more electronegative than other atoms. Therefore, a halogen atom withdraw the electron pair towards it and had to release the proton since the halo acids are more acidic than the normal acid. So here you can see this halogen is attached to this position, to the alpha position. As you know that these halogens are the are withdrawing nature, and they are more electronegative than any other atom. So these halo acids are more acidic. These halo acids are more acidic. These are more acidic than this carboxylic acid. So because its nature is withdrawing, they are more electronegative, and they will withdraw the electron pair from this carbon atom, and this carbon atom will withdraw electron from this carbon, and this will withdraw this oxygen, and from here this oxygen will withdraw electron from this hydrogen. So this hydrogen will move out from here, and there is a release of the proton from here. Since the halo atoms are more acidic than the normal acids. So here the same thing is shown here, that this halogen is withdrawing because of its electronegative nature. This halogen is withdrawing electrons from this carbon atom. This halogen is withdrawing electrons from this carbon atom, and this carbon will withdraw electron from this oxygen atom, and this oxygen will withdraw the electron from this hydrogen. So there is a removal of this hydrogen as a proton. It will get removed from here, and there is a form of this ion is formed here. So the acidic strength of this halo acids are more acidic. These are more acidic compared to the carboxylic acid because halogens are more electronegative. Halogens are more electronegative than other atoms. Halogens are more electronegative than other atoms. Therefore, a halogen atom withdraw the electron pair towards it and helps to release the protons since the halo acids are more acidic than the normal acids. So these halo acids are more acidic than the carboxylic acid because halogens are more halogen as compared to the carbon atoms or this carboxylic acid. These are more electronegative because they have the capability to withdraw electrons from the another atom. So they will withdraw electron. They will withdraw the electron pair towards it, and this helps to release the proton from this carboxylic acid. And since the halo acids are more acidic than the normal acid, so that is why these halo acids are more more acidic than the normal acids. The example is shown here how the halogen is withdrawing the electron and how the proton is getting released from here. Next is reaction due to halogen atom. So first was the acidic character of this halo acid. Now the reaction due to halogen atom. So first is your reaction with alkali. So in this you will see that the alpha halo acids undergo alkaline hydrolysis form and alpha hydroxy acid. So in this alpha halo acid undergo alkaline hydrolysis forms the alpha hydroxy acid. So here this is a halo acid, the alpha halo acid, and when it is reacting with the sodium hydroxide, that is a base alkaline, and there is a hydrolysis in this, and there is a formation of this. There is a formation of this alpha hydroxy acid, that is a hydroxy group gets substituted to this chlorine atom, and there is a formation of this alpha hydroxy acid because NaCl is formed. Second is your 2-bromopropanoic acid. So here the example is shown here. So we have taken here 2-bromopropanoic acid, and when it is reacting with this silver hydroxide, then there is a formation of this lactic acid. So here the lactic acid is formed here. So this is your CH3CHOSCOOH plus AgBr is formed here. So first, in the presence of this alkaline, that is your NaOH, sodium hydroxide, there is a formation of this alpha hydroxy acid, and from this alpha halo acids. And secondly, example is given here, the 2-bromopropanoic acid, and in the presence of this 2-bromopropanoic acid, when it is reacting with this AgOH, there is a formation of this lactic acid is formed here, and plus AgBr is formed here. So while alpha halo acids on reaction with alkali forms beta hydroxy acid and alpha beta unsaturated acid. So this alpha halo acid on reaction with the alkali. So when this alpha halo acid is reacting with this alkali, there is a formation of a beta hydroxy acid. So this beta hydroxy acid, from this beta hydroxy acid, there is a removal of the water molecule, and there is a formation of your alpha beta unsaturated acid. So in the method of preparation, we have prepared from the alpha beta unsaturated acid, this alpha halo acids are formed. So here the reaction is your reverse. So from this beta halo acid, when it is reacting with this alkali NaOH, there is a formation of this beta hydroxypropanoic acid, and this propanoic acid, here you will see this, here there is a attachment of this OH, and here this H. So this water molecule, whole water molecule will remove out from here, and there is a formation of this alpha beta unsaturated acid. This double bond is placed between this CH and the CH2. So there is a formation of this acrylic acid. So this acrylic acid is formed here. Next is a nucleophilic substitution reaction. So in the nucleophilic substitution reaction, the halogen group present in a halo acid can be replaced by the nucleophiles such as CN, NH3 or OC2H5. The nucleophile means here the electron, the electron donating species. Means this nucleophile has the capability to donate the electrons, and these nucleophiles, example is your CN, NH3 or OC2H5. In this they are substituting the another atom, and that is why they are nucleophilic substitution reaction. And the halogen group that is present in the halo acid can be replaced. So this halo acid is replaced by your replaced by your nucleophile, that is your CN, NH3 or O2 C2H5. These are the nucleophile because they are having the electrons present on it, means they are having the capability to donate electrons. That is why they are known as electrophile. So they are substituting the position of the halogen from the chain, and itself they are substituted on that position. So this is your CH3 CHCl plus KCl. That is your alpha chloropropanoic acid, and when it is reacting with this nucleophile, that is your potassium cyanide, then this cyanide will will substitute this chlorine with itself, that is your cyanide. So here this alpha chloropropanoic acid, when treated with this potassium cyanide, then there is a formation of this alpha cyanopropanoic acid. So this alpha cyanopropanoic acid is formed here on reaction of this alpha chloropropanoic acid with this KCN, and there is a formation of this alpha cyanopropanoic acid is formed here, because on the alpha position the chloro is substituted by the cyano group. So its name is alpha cyanopropanoic acid. Next is your CH3 CaCl COOH plus NH3. So in this, on the alpha chloropropanoic acid, this is also the same alpha chloropropanoic acid, and when it is treating with this ammonia, that is a nucleophile, it is having a electron pair present on the nitrogen, then there is a removal of the hydrogen from this, and means a proton is removed out from here, and this NH2 group, this amino group is getting attached to this C and replaced this chloro by the amino group, and there is a formation of this alpha amino propanoic acid is formed here. And from this H, which is removed out from here, this will get reacted with this HCl. There is a formation of this alpha chloropropanoic acid is formed here. So alpha amino propanoic acid is formed from alpha chloropropanoic acid by the treatment with the with the treatment with the as ammonia. This from this alpha chloropropanoic acid on the treatment of this ammonia, there is a formation of this alpha amino propanoic acid is formed here. Plus from this ammonia, the H is removed out and this proton is removed out and it gets attached to this chlorine. Next is your alpha chloropropanoic acid is reacting with the sodium ethoxide. So this alpha chloropropanoic acid is attached or is reacted with this sodium ethoxide, and there is a formation of this alpha ethoxy propanoic acid. So on the alpha position, this ethoxy is get attached, and this Na. Then when this sodium ethoxide is dissociated, then there is a formation of this sodium Na positive and O(C2H5 negative, and from here the Cl is removed on, and the Cl when removed on, it get attached to this sodium. So there is a formation of NaCl, and this O(C2H5 it get attached to this chlorine. Then there is a formation of this alpha ethoxy propanoic acid is formed here. So this is the nucleophilic substitution reaction in which the nucleophile is replacing this halo from the halo acids, and there is a formation of these products. Firstly, it is the alpha cyanopropanoic acid is formed here when this alpha chloropropanoic acid is reacted with this KCN. So there is a formation of this alpha cyanopropanoic acid. Secondly, when the ammonia is reacted with this alpha chloropropanoic acid, then there is a formation of this alpha aminopropanoic acid is formed here. And thirdly, when this alpha chloropropanoic acid is formed, when it is reacted with this sodium hydroxide, sodium ethoxide, then there is a formation of this alpha ethoxy propanoic acid is formed here, plus NaCl is formed. So thirdly is the reaction due to the COOH group. So here the reaction with the COOH group. So the first reaction in this reaction due to the COOH group is your action with NaHCO3, that is your sodium bicarbonate or sodium carbonate. So we are reacting this halo acids with this sodium bicarbonate or sodium carbonate, that is your NaHCO3 or Na2CO3. So on reaction with the sodium bicarbonate or sodium carbonate, halo acid decomposes to release carbon dioxide. So here the halo acids are decomposing and there is a release of this carbon dioxide from here. So this chlorine, this is your chloroacetic acid, and when this chloroacetic acid is reacted with this sodium bicarbonate, there is a formation of this sodium chloroacetate is formed here, plus CO2 is released out, plus H2O is formed here. So a salt of this acetate halo acid is formed here, and plus CO2 is released out, plus H2O is formed here. Again, when this chloroacetic acid is reacting with this sodium carbonate, so there is a formation of this sodium chloroacetate, and there is a formation of this CO2 plus H2O is formed here. So this chloroacetic acid plus Na2CO3, there is a formation of the sodium chloroacetate plus CO2 plus H2O is formed here. Secondly, the reaction with the alcohol. So in the reaction with the alcohol, these halo acids are reacting with the alcohol, and there is a formation of the ester. So the ester is formed here. So this halo acid is reacting with this alcohol, that is a chloroacetic acid, is reacting with this C2H5OH, that is your or ethanol, and when there is a formation, and there is a formation of this ethyl chloroacetate is formed here, plus H2O is formed here. So this chloroacetic acid plus ethanol is reacted, and there is a formation of this ethyl chloroacetate is formed here, and water molecules react. These water molecules removed out from here. So there is a formation of this acyl group. So then an acid and then alcohol is reacting, then there is a formation of this asteroids. The next is your reaction with your PCl5, that is your phosphorus pentachloride. So in this, the reaction with pentachloride, they also react with PCl5 to form the acid chloride. So this chloroacetic acid is reacting with the PCl5, and there is the formation of this chloroacetyl chloride plus POCl3 is formed, and plus HCl is formed here. So the chloroacetic acid is reacting with the pentachloride, phosphorus pentachloride, and there is a formation of this chloroacetyl chloride. So this is the derivative of this carboxylic acid is formed here, plus POCl3 is formed here, and HCl is formed here. So there is so in the reaction due to the COOH group, firstly the action with the sodium bicarbonate or the carbonate. So in reaction with the sodium bicarbonate or the sodium carbonate, these halo acids decomposes, and there is a formation of this carbon dioxide. Means the carbon dioxide is evolved out from here. So there chloroacetic acid is reacting with this sodium bicarbonate. There is a formation of this sodium chloroacetate plus CO2 plus H2O is formed here. Again, when chloroacetic acid is reacting with this sodium carbonate, there is a formation of this sodium chloroacetate plus CO2 is formed here plus H2O is formed here. Again, when the reaction with alcohol, these halo acids react with alcohol, and there is a formation of the esters. So this chloroacetic acid plus C2H5OH means the chloroacetic acid is reacting with this ethanol. In the presence of an acid, there is a formation of this ester is formed here. So this ethyl chloroacetate is formed here plus H2O is formed here. Again, when the reaction with PCl5, so in the PCl5, they are also reacting these halo acids. Alpha halo acids are also reacting with the phosphorus pentachloride, and there is a formation of this acetyl chloride is formed here. Plus POCl3 plus HCl is formed. Next is your hydroxy acids, that is a malic, tartaric, and the citric acid. So here these hydroxy acids contain a OH group and a COOH group. They may be mono or polybasic. Means here that the hydroxy acids are containing the OH group as well as the COH group on the aliphatic chain. So here the monocarboxylic acid are classified as alpha hydroxy acid, and the beta hydroxy acid or the gamma hydroxy acid, delta hydroxy acid, depending on whether the OH group bonded to the alpha, beta, gamma, and the delta carbon atom of the hydrocarbon chain with respect to COOH group, and the glycolic acid, lactic acid, tartaric acid, malic acid, citric acid, mandelic acid, etc. are alpha hydroxyl acid, while salicylic acid is your while salicylic acid, beta hydroxybutanoic acid are beta hydroxy acid. And alpha hydroxy acids are naturally occurring carboxylic acids found in many foods, including glycolic acid, lactic acid, citric acid, and malic acid, among others. So the most commonly used alpha hydroxy acids are glycolic acid and the lactic acid. So these hydroxy acids, these are containing the OH group as well as a COOH group. That is why it is hydroxy and acid. So they may be a mono or the polybasic, and the monocarboxylic acid, these monocarboxylic acids, these are classified as alpha hydroxy acid. So this monocarboxylic acid means there only one carboxylic acid is attached to the hydrocarbon chain, and they are classified as alpha hydroxy acid, beta, gamma, or the delta hydroxy acid. Depending on the position of this OH group present on the carbon chain, hydrocarbon chain. So whether if the hydroxy group is present on the alpha position, then it is known as alpha hydroxy acid. And if it is present on the beta hydroxy position, then that is known as your beta hydroxy acid. And if it is present on the gamma position, then it is known as gamma hydroxy acid. And if it is present on the delta position, then it is your delta hydroxy acid. And depending on whether the OH bonded, it depends on whether the OH group bonded to the alpha, beta, gamma, and delta carbon atom of the hydrocarbon with respect to the COOH group. And these glycolic, lactic, tartaric, and malic and citric acid, this mandelic acid, these are all are the alpha hydroxyl acids. And salicylic acid and beta hydroxybutanoic acid means on the beta position, this hydroxy group is attached on this butanoic acid. So these are the beta hydroxy acids. And the alpha hydroxy acids are naturally occurring carboxylic acid found in many foods. So these carboxylic acids are also present naturally. So this alpha hydroxy acids, they are also present in the are also found in many foods, while glycolic acid that is present in your sugar cane, lactic acid is present in your milk, citric acid is present in the citric fruit, and the malic acid is present in the apples. These are among the alpha hydroxy acids that are present naturally. These are occurring naturally carboxylic acid that are found in the many foods. And the most commonly used alpha hydroxy acids are glycolic and lactic acid. So that the commonly used alpha hydroxy acids are your glycolic and the lactic acid. The glycolic acid that is present in the sugar cane, and the lactic acid that is present in the milk. This is the common name of some hydroxyl acids. So here the chemical formula is a CH2OH COH. So in all these structures, you can see that only one carboxylic acid group is present. That is why they are known as monocarboxylic acid. And in the first CH2OH COOH, in this you can see that on this the first the carbon is present on the alpha position in respective to this carboxylic acid. So this hydroxy group is present on this carbon, first carbon in respective to this carboxylic acid. So its name is hydroxyl acetic acid. So this is your hydroxyl acetic acid because there is only one carbon atom is present. Its name is your hydroxyl acetic acid. Next is your CH3CHOH COOH. In respective to this COOH, this hydroxy group is present on the first carbon among the two carbon. So this its name is alpha hydroxy propanoic acid. So it is present on the alpha position. The hydroxy group is present on the alpha position. So its name is alpha hydroxy propanoic acid. Next, in the next, you can see here that this OH group is attached to the beta position of this hydroxy, hydroxy. So this is known as beta hydroxy propanoic acid. This is your beta hydroxy propanoic acid. Its name is beta hydroxy propanoic acid. Now the fourth is your CH2OH, CH2, CH2, COOH. In this, the hydroxy group is present on the delta position, that is your in respective to the COOH, alpha beta gamma position. So there its name is gamma hydroxybutanoic acid. So these are the name how we are nomenclating this hydroxyl acids. And first method is your preparation of alpha hydroxy acid is your the hydroxyl carboxylic acid are synthesized by using different methods. Like the first method is your by the hydrolysis of alpha halo acid. So alpha hydroxy acid can be prepared by the alkaline hydrolysis of alpha halo acid. So here you can see this is your alpha halo acid. So this is reacting with this NaOH and there is a formation of this alpha hydroxy alpha hydroxy acids. And plus NaCl is formed, and the lactic acid is obtained by the alkaline hydrolysis of the alpha bromopropanoic acid. So this is your 2-bromopropanoic acid or your alpha bromopropanoic acid, and when we are reacting it with this silver hydroxide, so there is a formation of this lactic acid is formed here. So the lactic acid is your or OH and the COOH. So there is a formation of this lactic acid. Second method is your by the action of nitrous acid. So in this, the alpha aminopropanoic acid is on treatment with this nitrous acid in presence of this sodium nitrite and hydrochloric acid. There is a formation of this alpha hydroxy acid is formed here. So here the alpha aminopropanoic acid is reacting with this nitric and nitrous acid in the presence of sodium nitrite and HCl. So there is a formation of this lactic acid is formed plus nitrogen plus H2O is formed. Next is the by the hydrolysis of cyanohydrine. So this alpha hydroxy acid can be obtained by the reaction of aldehyde with cyanohydrine followed by the acetic acid hydrolyzed. So this acetaldehyde first is reacted with this hydrocyanide, then there is a formation of this acetaldehyde cyanohydrine. After that, this H2O and H plus, there is a formation of this lactic acid. Next is the by the reduction of keto acid. So this alpha hydroxy acid can be obtained by the reduction of ketonic acid in the presence of this sodium and Hg, and there is a formation of this lactic acid is formed from this alpha ketopropanoic acid by the hydrogenation or by the reduction. Next is the preparation of beta hydroxy acid. So like alpha hydroxy acid, beta hydroxy acid can also be synthesized using this following method. So first is your from chlorohydrin. So beta hydroxypropanoic acid can be produced on the reaction by the reaction of this ethylene chlorohydrine with sodium potassium cyanide followed by hydroxyl. So this ethylene chlorohydride when reacted with this potassium cyanide, there is a formation of this chlorohydrine is formed here by the reaction of this intermediate is formed here, and when this is hydrolyzes, is a formation of the beta hydroxypropanoic acid is formed. So next is your quotients. So which of the following is basic? So the basic is your first CH3, CH2, OH is your basic. Next, acetamide is treated separately with the following measure. Which of the following is formed? So NaOH plus Br2. Hydrogenation of benzoyl chloride in the presence of PD on BaSO4 gives B, that is your benzaldehyde. Next is your benzoyl chloride is prepared from benzoic acid. By this SOCl2. Next, when propanoic acid is treated with aqueous sodium bicarbonate, CO2 is liberated. The C of CO2 comes from bicarbonate group. Next, benzoyl chloride is prepared from benzoic acid by the SOCl2. Next, this is the reaction. Here, what will be formed? The ester and water. No, ester and water is formed here. So acetamide is treated separately with the following reagent, and which one of these would be the methylamine? So this is your B. So these are some of the references from where you can study this topic, or you can study or you can learn this topic. And thank you so much for this lecture.